Hey everyone, it's Mr. N here, and this is the 2017 last minute review, things you guys had questions on that you had asked me about. So I'll put this together for you, so let's go ahead and get this done. Number one says, a company has started selling a new type of smartphone at the price of $110 minus 0.05x, where x is the number of smartphones manufactured per day. The parts for each smartphone cost $50, and the labor and overhead for the plant costs $6,000 per day. How many smartphones should the company manufacture and sell per day to maximize the profit? And we are reminded here that the profit equals the revenue minus the cost. Well, let's take a look at what our profit equation is. We need the profit to be the revenue, so we need revenue, some sort of revenue in here. And our revenue is going to be each smartphone we sell at this price. So suppose I sold 100 smartphones at $110 minus 0.05x. That's my revenue equation. So 100 smartphones at this price. Now we need to find out what our cost is, and it tells us our cost is $50 per day, and along with labor and overhead. So for each smartphone, it's $50 per day along with labor and overhead. So that would mean 50x plus 6,000. Well, our profit is going to be our revenue minus our cost. So what we take in minus what our expenses are, that's how much money we make. And we're going to put this together, and we end up with x times 110 minus 0.05x times 50x plus 6,000. Now we can go ahead and we need to maximize our profit. So we have to take a derivative here. Well, let's see if we can clean this up a little bit. You can FOIL it out. You can just distribute this x, which would make it easier to take the derivative. So we could say 110x minus 0.05x squared times our 50x plus 6,000. And then we could take the derivative at this point and set it equal to 0. So we're going to have the first times the derivative of the second plus the second times the derivative of the first. So in this case, if you did take the derivative, you would end up with 110x minus 0.05x squared. So the first times the derivative of the second, which would be 50, plus the second, which is 50x plus 6,000, times the derivative of the first, which is 110 minus 0.0, or 0.01, or it would be 0.1 in this case. 0.05 times 2 would be 0.1 x. And then we have to set this equal to 0, find the critical points, and determine where there's a max or a minimum. You could, at this point, this would be like on a graphing part, if it's on a graphing part of the calculator. You could graph this and do the end derivative graph and then see where that's 0, or you could graph your derivative and see where those zeros are there. Well, it's going to end up kind of looking like this shape, and it's going to cross over here at 600. And if we put this on a number line, we see that the slopes are at 600. The slopes are positive, then they go negative. So that means we have our maximum. And you could test endpoints in this, but the endpoints, if we examine this, are going to be 0. We don't make anything, or as many as we want to make. There's no limit on how many we can make, so it'd be out to infinity. So we're going to go ahead and stick with this, and I'm sorry, this is at 600 here. So we're going to say our max profit occurs at x equals 600 smartphones. All right, moving on to number 2. Let's take a look at this one. A rancher wants to construct 2 identical corrals using 800 feet of fencing. The rancher decides to build them adjacent to each other so that they are facing on one side. What dimension should the rancher use to construct each corral so that together they enclose the largest possible area? Again, this is an optimization. We want to optimize this area. So I've got this corral, but there's 2 identical corrals, so we'll just cut it like that. And suppose we use x for each of these sides of the corral for these fencing parts. Well, then this, we have 800 total, would be the 800 minus the 3x, but I've got two sides. I've got this side right here and the top side, so I need to divide it by 2. So each of these are 800 minus 3x over 2. So the area would be x right here times this whole side, 800 minus 3x over 2. So that's our length. This is our width. Well, we can clean this up a little bit. We end up with 400x minus 3 halves x squared. Our domain here is I cannot use any fencing, which is 0, all the way out to, well, I'm not limited. It would have to be, I could say 800. I shouldn't really put infinity because I'm limited to 800 feet of fencing. And if I use 0, I would have to use all 800 on the other ends, but that wouldn't work out. So our limit here would be we could say if you use 0, the other endpoint of the domain, since we're not equaling it, would be 400, because 400 here, 400 there to make 800. So we could go out to 400. All right, let's take a look. If we use 400, again, think about it, we're not going to have any sides. If we use 0, we're not going to have any length and width sides. So obviously the endpoints of the domain in this case won't matter so much. All right, so now let's go ahead and maximize this area. So I'm going to take a derivative. So I end up with 400 minus 3x, and I want to set this equal to 0. So I end up with x equaling 400 over 3. And you can test this on a number line, 400 over 3. And you'll get positive slopes here, negative. So yes, we do have a maximum at this point. And in our case, this is going to be our absolute. In fact, think about it. This is going to be an upside down parabola when you graph this, right? This area right here. So let me highlight it one more time for you. This is going to be an upside down parabola, negative x squared. So we will have a maximum on it somewhere. All right, so now this ends up being our maximum. So we have the length, or we said the width in this case, is going to be 400 over 3 by, well, let's plug that in, and you'll end up with 200. And this is feet. 400 by 200 feet. So in other words, this is going to be 400 over 3, these parts right here, and these will be 200. All right, moving on to number 3. So for this one, it says, let f of x equal 3x squared plus 1 for x less than 0, 1 minus sine x for x greater than or equals 0. Which of the following statements is true about f? Does the limit exist? Is it continuous? Is it differentiable? Well, if it's differentiable, it's got to be continuous. So let's just go ahead and take a look at some parts here. Let's first see if it's differentiable. Is it differentiable at 0? In other words, if I take the derivative, will it occur at 0? If I take the limit, let's go back to the limit here. I would need to examine this from the left, from the right. If these two are the same, then I can conclude that. And if f of x equals all this, then I can conclude that it's continuous and the limit exists as well. So if I put in 0 right here, I will get f of x equals 1. If I put in 0 right there, I will also get f of x equals 1. So the limit from the left and the right is the same. And f of 1, let's see, so the limit from the left is equal to 1. Limit from the right is equal to 1. And then f of x, when I examine f of x, as x goes to 0, I would have to plug it into here. This is where it equals 0. And I get 1. So all this works. So we know the limit exists. We know it's continuous. Is it differentiable? Well, let's think about this. I'm working with a parabola, a parabolic function that goes into a sinusoidal, negative sinusoidal function like that. I'm going to end up with a kink right there. So it is not differentiable because it has a kink. It will not be a smooth transition. So parabolic to sinusoidal, so it's to a sinusoidal jump pretty much. and not jump, but abruptly like that. So that's going to form a kink. So in this case, we're going to, there's another way to do this problem, but that's probably the best way that I can see for you guys to visualize what's happening and why it's not differentiable, because it has that kink there. So for this one, our only answers are 1 and 2 only, so this answer is D. You can also consider for to see if it differentiability, you can take the derivative of this, and you're going to get 6, oops, you're going to get 6x when x is less than 0, and you will also get negative cosine x when x is greater than or equal to 0. If I examine the limit as x goes to 0 from the left and the limit as x goes to 0 from the right, from the left I'll end up getting 0. From the right I'll end up getting negative 1. Therefore, it's not continuous there. That's another way you can think about this. Okay, moving on to number 4. Here we have the radius of a sphere is decreasing at a constant rate of 3 centimeters per second. In terms of the surface area of the sphere, S, what is the rate of change of the volume of the sphere in cubic centimeters per second? So we're looking for a rate of change of volume. So we know a volume of a sphere is 4/3 pi r cubed. So if I want a rate of change, I need a dv dt, so I need to differentiate this, and that's going to give me 4 pi r squared dr dt. I know that the surface area is equal to 4 pi r squared. And we're going to just call this S because they said the sphere S is going to be S. And in this case, they're telling me that the radius of the sphere is decreasing at a constant rate. So dr dt, these are all my givens. This is every single thing I know. Dr dt is going to be negative 3 centimeters per second. All right, well, let's see. This can go straight into here. This can go straight to there because they say in terms of the surface area. That's my 4 pi r squared. So that means dv dt is going to be S times my negative 3. So negative 3s would leave me with C as my answer on that one. All right, for the next question, number 5. Let f be the function defined below. Which of the following statements about f are true? So f of x is equal to x squared minus 9 over x minus 3. That should right there. That should stand out to you that you can do this. X minus 3, x plus 3 over x minus 3. And you know that there is a hole at x equals 3. And we're told at 3, that hole, the value of it is equal to 1. All right, so let's see. Does f have a limit? Is it continuous? Is it differentiable? So for this one, we know it has a hole at 3. So let's find what is f of, let's find the limit. Let's start with finding the limit. The limit as x approaches 3 from the right and the limit as x approaches 3 from the left. Well, from the right and from the left, I'm going to get, when I come in here from the right, we're going to get a value bigger than this right here. So we'll get, say, 9.1 over 9.1 over 3.1 minus the 3 and then not minus the 9. So you get like something like 0.1 over 0.1. And if you approach it from the left, you're going to get the same thing. You're going to get negative on top, negative on bottom. Those cancel each other out. So you'll end up with these two limits equaling the same value. So that tells me it does have a limit. But it's not continuous because we know that there's a hole there. And because of that hole, it's not going to be continuous or differentiable. But what we can do is take a look. If we actually did find this limit, you can L-hop it. If you really wanted to find this limit right here, L-hop it, and you would end up with 2x over 1, and at 3, the limit at x approaches 3, 2x over 1 would give you 6. So these we know from the left and from the right, it's going to be the same 6. But then at f of 3, I get a value of 1. So I do have a hole there and the value like this. So that's what we're looking at. So it's not continuous, it's not differentiable, but it does have a limit of 3. So this one would be a 1 only. Okay, so now looking at number 6, we've got the limit as h goes to 0 of ln of 2 plus h minus ln 2 over h. Well, one thing we realize here is that this is the definition of a limit. This is how it's structured, the limit as h goes to 0 of f of x plus h minus f of x all over h. So that's the way it's structured. So what this question is really asking us is we need to find the limit of this, which is really just the derivative of the natural log of x. So that is 1 over x, and we need this to occur at the value of 2, so that gives us 1/2. So that's how we do this problem. So the next one, number 7, the limit as h goes to 0 of the sine of pi over 2 plus h minus 1 over h. Now, this is, again, similar to what we're looking there. We're looking at the definition of limit, and this is the sine of x at pi over 2, because the sine of pi over 2 is our 1 value, so that matches up. So we need to take the derivative of sine of x at pi over 2. Well, the derivative of this will be equal to the cosine of x, and we need to plug in the value at pi over 2, so the cosine of pi over 2 comes out to be 0. So that's the answer for number 7. All right, moving on to number 8. Number 8 says the region bounded by the curves f of x equals cosine pi x minus 1, and g of x is x times 2 minus x. So right away we can look at this and say that we know that this is 2x minus x squared. So this is the parabolic one. So this is our g of x function, and this would be our f of x function. We need to find the area of the region R. So to find the area of the region, we're going to take the top curve minus the bottom curve over the bounds. This is our region R. So we're going to take it from the top curve minus the bottom curve. Those will be our slices from 0 all the way to 2. So all of these. So in this one, we will have the integral. We will have the integral from 0 to 2, because that's where they cross over here and right there, of the top curve g of x minus the bottom curve with respect to x. And working this out, we're going to have the integral from 0 to 2 of 2x minus x squared minus the cosine of pi x minus 1 dx on this. Okay, so we can clean this up a little bit to be 0 to 2, and then we're going to say 2x minus x squared minus cosine pi x plus the 1 dx. We integrate this, which will give us x squared minus 1/3 x cubed minus 1 over pi sine pi x plus x on the bounds from 0 to 2. So the integral of cosine pi x is going to be 1 over pi times the sine of pi x. Plugging in our values here, we will end up with 4 minus 8/3 minus 0 plus 2 minus 0, which gives us a final value of 10/3 square units. Okay, so for part B, it says a solid has a base R and the cross section is perpendicular to the x-axis, so we're taking cross sections this way, is an isosceles right triangle whose hypotenuse lies in R. Set up but do not evaluate an integral for the volume of this solid. Alright, so what we've got here is we are taking cross sections perpendicular to the x-axis, and these are isosceles right triangles. So we have our isosceles right triangle right there, so these will be 45, 45. And since we've got this situation, So in our hypotenuse right here, that for this isosceles right triangle will be this length, since it's saying the hypotenuse lies in R. So this is that. So that means the hypotenuse is made up of the top curve minus the bottom curve. That's our hypotenuse. So we need the area of this triangle. And the area is 1/2 times the base times the height. Well, if this is an isosceles right triangle, if I call this h, that'll be h over root 2. So will that be h over root 2. So this ends up being 1/2 h over root 2 times h over root 2, which ends up being 1/4 h squared. So now, the volume is going to be the integral of the area, which is going to be the integral from 0 to 2, and the area is 1/4, and the hypotenuse we know as being the g of x minus the f of x squared dx. So that is our volume. Now it says do not solve for this, but let's just clean it up a little bit so it looks a little cleaner. So we're going to say the volume is going to be 1/4, the integral from 0 to 2, and then we could put in our equations here if we want. This will be 2x minus x squared minus the cosine pi x plus 1 dx. This would be squared. So that is our volume for this cross-sectional region. All right, for part C, we have a solid whose base is R, and the cross-sections perpendicular again to the x-axis are a semicircle, and the diameter lies, whose diameter lies in R. So this time we've got these semicircles, and these are the semicircles coming out like this at you. So since these are the ones coming out at you, that's what I'm going to take a look at. And in this case, I know that the area of a semicircle is 1/2 pi r squared. Well, this radius is not quite the whole g of x minus f of x. It's half of that. So the radius is 1/2 of the g of x minus the f of x. So now that we know that that's our radius, we can combine this and say that the area is 1/2 pi times 1/2 g of x minus f of x squared, like that. Oops, I need the squared on the outside, sorry. Let's fix that, squared. So there's my radius squared. All of this will clean up to yield 1/8 pi times g of x minus f of x squared. So now let's just put this in our volume formula. Volume is going to be the integral of the area, so our volume, we integrate that area. So this will be on the bounds from 0 to 2, 1/8 pi times g of x minus f of x, this squared dx. Now you can put the 1/8 pi out in front, and 0 to 2, and I'm just going to go ahead and leave it in this form, g of x minus f of x. We know what the equations are. They are above over there. So we'll just leave it like this for now. All right, moving on to part D. Part D, again, set up, but do not evaluate the integral for the volume of the solid when R, this region, is rotated about the line y equals 3. So if we take a look at y equals 3, and we take a look at where this region is, let's move this down. So y equals 3 is up here. We're going to rotate this thing all the way around that. So we know that this, we're going to end up having to use a washer method with g of x being our little r, and then our big R is going to be the f of x. And so since our line of rotation is above it, we're going to say 3 minus that. So 3 minus the little r, 3 minus the big R. So our volume with shells is r squared minus r squared. Volume is pi times the integral of that. And so let's put this together now. We're going to end up with the volume as being pi on the bounds from 0 to 2. And this will be 3 minus r f of x squared minus, so this was our big R squared. Little r squared is going to be 3 minus g of x squared, and we'll put this in brackets and we're going to say dx. So that is our volume. Now again, our slices are perpendicular to the x-axis, that's why we chose dx, because these were perpendicular to the axis of rotation. I should say right here, dx. So that's why we chose our dx. So this is our volume for part D. All right, so let's move on to this problem. And on number 9 here, it says the temperature of the water in a swimming pool at time t is modeled by strictly increasing, that's important to know. Twice differentiable, that's also important to know. Function W, where Wt is measured in degrees Celsius and T is measured in minutes. At time t equals 0, the water in the pool is 20 degrees Celsius. The water is heated for 45 minutes. Beginning at time t equals 0, select values for between the first 30 minutes are shown in the table. So we've got a table for the first 30 minutes, and we know that it's going for 45 minutes though. And we know the initial is 20 degrees C. So that's at time t equals 0. Using the values in the table, estimate W prime of 10, show the computation that led to your answer. So this is the rate of change at 10 is what we're looking for. So since we don't have 10 in the table, we're going to take the two closest values. So we need W prime of 10 to be W of 12 minus W of 7 over 12 minus 7. And in this case, we're going to end up with 22.7 minus the 20.8 all over the 12 minus 7. So this gives us 0.38 degrees Celsius per minute. And this is the rate at which the temperature in the pool changes per minute. So that is what that comes out to be. All right, for part B, use the data in the table to evaluate the integral from 0 to 30 of W. So the integral of the rate of change, using correct units, interpret the meaning of this in the context of the problem. Well, what this means is this is FTC right here. And so what we want is the integral of the derivative of the integral. It works out to be the same. So what we're looking here to do is say W of 30 minus W of 0. That's what this problem is asking us to do. So we work this out, we get 25.8 minus the 20, which gives me 5.8 degrees Celsius. And this is, to interpret this, this is the change or increase. This is the change, and in our case, it's an increase. And we know it's strictly increasing, since we are told that right there, in the temperature so it's the change in temperature over the 30-minute period. Okay, looking at the next one. This one says, from 0 to 30, the average temperature of the water in the pool is given by that. All right, now we are to use write Riemann sum with 4 subdivisions indicated by the data in the table to approximate the 1 over 30, which is the average temperature over that time period. All right, well, let's take a look. What I want to do real quick is I want to show you something, because this is going to help us later. Let's just quickly plot what's happening. We know it's strictly increasing. So at 0, we're going to have a value here of 20. At 7, we're going to have a value of 20.8, so a little bit higher. At 12, we've got a value of 22.7, even higher. At 20, 24, and then at 30, 25.8. So I'm doing this to show you that this is strictly increasing something similar to that. So now if we wanted to do Wright-Riemann sums, well, with Wright-Riemann sums, what we're looking to do is our first rectangle will be like that. Our second rectangle will look like this, and so on. You can right away see, because this is our right endpoint, that we are going to get an overestimate. So we already know that this is going to yield an overestimate. So let's take a look at how we're going to do this Riemann sum. Well, the Riemann sum is the sum of the areas of the rectangle. So this is the sum of the delta x times my heights. So this is going to be my delta x, and those are going to be my heights of each of those rectangles. So let's go ahead and do the right side of this, and this will end up being 1 over 30, because I'm taking this average value, and then the first one is going to have a delta x of 7 and a height of 20.8. The second one will have a delta x of 5 from 7 to 12 and a height of 22.7. The third one will have a delta x of 8 and a height of 24.6. And then, so again, this is the 8, there's the 24.6. And then the last one here will have a delta of 10, my delta x, and will have a height of 25.8. Okay, working all this out, you're going to get, I'm going to spare you the details in between, 23.7967 degrees Celsius. And we said that this is an overestimate because we have a strictly increasing function with right sums. So you can sketch this right and show this like this, and there's the visual for it. So this is the over estimate for it. All right, let's do this next part, and this is very similar. It's the same thing, but this time they want us to use left Riemann sums, so let's go ahead and do this. So this time when I use left Riemann sums, I'm going to start here as my 0, and I'll be going like this. So again, we can see what's going to happen right now. Well, we go out to there. This is my fourth rectangle, and I'm going to get an underestimate because all these spots underestimate what's happening. So this will be 1 over 30, so right there. And the integral part is going to be my left Riemann sum, and this will be, the first one will have a delta of 7, because we're going out from 0 to 7, and a height now, instead of, before it was 20.8, this height will be 20. And then the next delta will be 5 and have a height of 20.8. And the next delta x will be 8 with a height of 22.7. Then we end up with 10 times the 24.6. Working all this out, again, I will spare you all the details, 22.3867 degrees Celsius. And this is an underestimate, again, because it's an increasing function with left sums. So you could show the visual for it again. There's my left sum, there's my left sum. So that's an underestimate. All right, the next one, using the midpoint rule. Now be careful. You can't add these two and tell me the average is going to be the midpoint. If it comes out to be that, that's great. But we have talked about this. The average of the left and right yields the trapezoid, not the midpoint. So be careful with that. And with a midpoint, we are not going to be able to determine if this is an under or overestimate, because it will vary depending on, even though if it's a strictly increasing function, it'll vary on how it increases, where those midpoints are. So it'll be something like this, or maybe if it's the midpoint between these two, like that. So it's going to vary. So this one I cannot determine. if it's an over or under estimate. So let's take a look here. For this one, the midpoints. So what I need to do is I need to take the average, say if I sketch this out, and this is at 0, and this would be at 7. So I would need to take the midpoint right there and do that. That would be the first one. So that's the midpoint between 0 and 7. So that is the value there. So this will have a delta x still of 7, but it's the what that midpoint between 0 and 7 would be. So in this case, we're going to end up with 1 over 30. Now let's do all these midpoints. Now I could take a half and say 1/2 and then add them all up, but I'm going to show you what I'm doing here. This is delta x is 7, and we're going to take the average of those two heights, this height and this height. That'll give me the middle of those two heights. So in this case, it's going to be the 20 plus 20.8 all over the 2. That's half that average. So that's the average of those two heights. The next one has a delta x of 5, and we're going to take the average of those two, which will be 22.7 plus the 20.8 all over 2. The next one, the average of that, delta x is 8, and we've got 24.6 plus the 22.7 over 2. And then the last one has a delta x of 10, and this is in our table here, this is going to be the 25.8 and the 24.6, and then the 25.8, the average of those. Okay, to spare you all the details from in between doing this calculation, you end up with 23.09167 degrees Celsius. And again, we cannot determine if over or under estimate. All right, moving on to the last part of this, well, to the next part of. So now we have to use a trapezoid rule. So again, let's take a look. If I've got this increasing function, and here is time t equals 0, if I were to draw a trapezoid, just draw one large trapezoid, just to show you what's going on. Is that going to give you an over or under estimate? It's definitely going to give you an over estimate because it's an increasing function and I connect these 2 points. So this ends up, since it's strictly increasing, it's going to end up giving me an over estimate. So what we are looking to do here is we are going to create our trapezoids. So this, if you look, will be the delta x, which in our case is going to be the height, and these two parts will be the base. So that's just a quick rundown and review of how we did the trapezoid rule. So we needed the sum of 1/2 times the base times the height, right? Sum of the bases, which is, in our case, 1/2 of the delta x, which is our height, and then these bases. All right, so this leads to the following. We were going to say 1 over 30, because that's what it asks us to do. And then I'm going to take this 1/2 out. And now I'm going to do the delta x's right here times the sum of the bases. So for this first one, my delta x is 7. My two bases are 20 and 20.8. My second trapezoid, delta x is 5, and I've got 20.8 plus 22.7. My third will have a delta x of 8 and 22.7 plus 24.6. And the next one will have a delta x of 10, and I'll end up with 24.6 and 25.8. All right, working all this out, we end up with 1 over 60, and I'm going to spare you the detail. Well, here, I'll give you these values in between. 142.8 plus 108.75 plus 189.2 plus the 252. And all this will come out to be 23.09167. It came out to be the same exact thing, and we said this is an overestimate. Overestimate because in strictly increasing function. strictly increasing function, and we have a trapezoid rule on this. So again, you can show that this is increasing and we've got the trapezoid going on. So we are going to end up with an overestimate. Now, if you take the midpoint rule, you see that it comes out to be the same in this one. Now, if you take the left and the right, take those Riemann sums, average them, you will get this 23.09167. All right, for the last part, we've got on 30 to 45, the function W that models the water temperature is given by, the derivative is given by this. So it's important to know that the derivative is given by that. Based on this, what is the temperature of the water at time t equals 45? So at time t equals 45, we have a temperature from our table, or I'm sorry, at time t equals 30, we have a temperature from our table that was 25.8 degrees. So we want to take this 25.8 degrees and add it to what has changed. Well, this is our rate of change, but we want to know what it would be from the 30 to 45. So this is our W of T. This will give me the temperature from 30 to 45, that total temperature. So in this case, we're going to end up with 25.8 plus this, when you integrate, comes out to be negative 3.684479, which comes out to be 22.1155 degrees Celsius. So it looks like this, since it had started coming down, this function brought the temperature down a little bit. Which I guess that contradicts that strictly increasing part. So I guess we should have said in the original problem that it's strictly increasing from 0 to 30 minutes, and then that's it. From there on, it doesn't matter. So that's what we should have said in that initial part of the problem. But anyway, hopefully this review has helped. Make sure you study, go over these, and good luck.